Afternoon, everybody, or evening, or morning. Uh, Today is November 17th, and this video will be going over what the start of the week was about. This is week 14, by the way, right before Thanksgiving break. Today in this video, we're going to cover um, up to what was covered in class today. So that will be the notes on thermal energy, as well as questions 1 through 4 on assignment 9. So first things first, though, we'll get our week's announcements out of the way, and then get started on those notes. Um, Interesting. Your look. So first thing I want to make you aware of is the week 15 report card just ended, and so we're in that final stretch. There are 10 days left, actually 9 now, of either odd or even classes, and so we're really in that home stretch. Um, So in between that time, I want you to be aware that you still can update your work. You can turn in old work and make sure your grade is updated for the 20 week. Second announcement, there is a fundraiser going on this Friday for the class of 2022 at the Panda Express located next to the Vallarta on the Topanga and Roscoe. The really big Vallarta, you really can't miss it. So if I got 100 people to get to that fundraiser, they each buy like $10 worth of stuff. That's like Panda Express would make 1,000, and your class of 2022, would make almost $200. Obviously, you would hope for more people to go, but the goal is the same. If you want a nice prom, if you want a nice, I don't know, homecoming by 2022, graduation ceremony, you should really help your class out. And then the third announcement is an informal one. I'm now a club sponsor for the Future Health Professionals Club. If you're interested in joining, I'll send you a form to fill out, and then you'll just be a member on the roster. So if you're interested, shoot me a message on Schoology, and I'll reach right back out to you, and we'll get signed up. Now, what are we doing this week? This is week 14. Here's our agenda. We just covered the first day. So we finished the 16th and the 17th. So between now and then, we finished off the notes on thermal energy, and we got started on assignment number 9, the flow of energy. On Wednesday/Thursday, we'll continue off on assignment 9, and then if we get to Friday, we either might do some notes or some digital media kind of things. Now, last Friday, assignment 7 was due, so I'll be checking those notebooks throughout the week to see if assignment number 7 is done. And then on this Friday, I'll be repeating that process again for assignment number 8. And then Thanksgiving break. Now, use the break however you wish. If you want to turn in late work, old work, let me know. I will not very frequently check my email, so Remind would probably be the best way to do that. Close that off. We're done there. Close that off. So on Schoology, you'll find the notes for thermal energy and the flow of energy. Copy and paste those documents into your notebook, and we'll get started here. Assignment 7, here's assignment 8. And moving on to our notes on thermal energy. These are already completed. And so with our notes, we have a couple topics. We have a heating curve, and then later on, we'll do a phase diagram. For this heating curve, what we need to recognize is that we have temperature versus heat. These are two different concepts. Heat and temperature, while related very closely, are different concepts. As you add heat, right, your ice will eventually turn to water, which will turn to steam. You could also go the other way around, right? Take away heat, steam turns into water. Take away more heat, it turns back to ice. Now, these long flat lines represent the idea that if you have ice, it doesn't immediately turn into water. You have to wait for all of the particles in ice to break their bonds and then turn into water. That's why you have a long straight line. The heat needs to go through and affect every single particle. Same thing for water turning into steam. All of those bonds have to break. It doesn't happen immediately. It takes some time. And so what do these long flat lines represent? They represent times when those particles of water are gaining and losing energy in order to fully change phases, right? If you've ever boiled water, you know it takes a minute for that water to fully start boiling. You'll see a few bubbles, right? And then check back later. Now you got that roiling kind of boil going. Our phase diagram is one of the more complex looking diagrams, but it's to show a couple of things. Let me go ahead and annotate here real quick. We have gases, and so gases represent almost 50% of this diagram. Liquids represent, I would say, like 20%. It's not a very big chunk. And then solids represent maybe like another 30%. And so most particles you'll see are gases that are in the form of gases, right? Regardless of temperature, you have gases that exist at every phase, at every temperature. If the pressure increases, those gases get condensed and are turned into solids. And if the temperature is high enough, then they'll turn into liquids, right? The pressure, those particles will kind of start flowing past each other. And if the pressure and temperature increase to such a point, you'll end up getting something called a critical point, which is where our plasmas are made. Now, in these boxes, we have the terms and vocab to describe what those processes are called. So if a solid turns into a liquid, you melt it. If the liquid turns into a solid, you freeze it. The liquid turns into a gas, or vice versa, boiling or condensation. And the last two are the ones that aren't as common, but sublimation and deposition. So if you've ever seen dry ice is a solid and it turns into a gas at pretty much room temperature. So if you'd ever take like that dry ice as carbon dioxide, it turns immediately into a gas, and that's why you see that fog coming out. Alcohol, it's a liquid that vaporizes very quickly. So if I solidified it, if I cooled it down, it would vaporize just like that. Deposition is the other way around. Gas turning directly into a solid. So we're moving on. And I'm speeding this along because we cover this in class at length. And so just moving right along. The triple point is the pressure and temperature needed to get all three phases existing at the same time. And so that's where the value of this comes from. It allows us, the phase diagram allows us to predict the phase of a substance based purely on pressure and temperature. Most commonly for water, but other substances have their own phase diagrams, and they're useful because they let us predict how certain substances will behave at certain temperatures and pressures. So why is there no liquid phase at very low temperatures? So if we look at the low temperatures right around here, we see that they're either solids or gases. No liquid. Now, why would that be the case? Well, at low temperature, we have to remember they have low energy. And so those particles that are zooming around just kind of stop and they float in place. And so that's the gas, right? And as soon as you add any kind of pressure to that kind of minimal energy environment, they'll just kind of condense. They're not going to have enough energy to move around, so it's either going to be a solid or a gas. And so the liquid phase is kind of rare in that sense. In the universe, liquid water is very rare on like planets because it's either a solid or a gas. It's always noteworthy whenever we find liquid substances in space because it is just so rare. All right, moving on. Number 6. Why will it take longer to cook foods at higher elevations like Mount Everest? And so the question I asked in class has to do with this. At ground level, the pressure is kind of high. And when you go up into like Big Bear or any kind of mountaintop, the pressure tends to what? Increase or decrease? In class, we answered it was decreasing. And so let's kind of just throw up a fancy little image here. Let's say this is our planet. Right? Here is you, or me, or anyone. Hello. right? So on our planet, we have our atmosphere. There's layers on layers of the stuff. We have our atmosphere, there it is, and it's all kind of pressing down on you. That's a lot of pressure. Well, let's say you climb a mountain. Here's a mountain. Here's a bigger mountain. And say you're on that mountain. And then you're at the tippy top of this mountain. There is less pressure each time, right? So in this case, you have all of that pressure on you, all this pressure on you, very minimal pressure. So the pressure decreases as you go higher up because there's less and less air around you, not just oxygen, but air. And so if this is the case, at higher and higher temperatures, higher and higher, lower and lower pressures, my bad. At lower and lower pressures, let's say this, you're at ground level, right? If you're at ground level, if you boil a liquid, right, if you increase the temperature of a liquid, it stays a liquid. But if the pressure decreases, your liquid is gonna turn into a salt or into a gas pretty much immediately as soon as you start to boil it. So if you're trying to cook some noodles or pasta up on like a mountaintop, you're gonna need more and more water. And if you need more and more water, you need to cook it for longer because otherwise their water's just gonna boil away. And so to answer this question, why does it take longer to cook foods at higher elevations? The reasoning is the pressure is so low, water boils away so much faster. So you need more water to cook food, which means you need more fuel, which means everything's just going to take longer and longer. Okay. With that said, we're now moving on to assignment number 9, and I'll only cover the first half of the stuff that we covered in class today. So with assignment number 9, we started off with the vocab. The vocab for number 5 is conservation of energy. Number 6 is specific heat capacity. Do this on your own. The vocab terms are in the book, they're highlighted. And for this assignment, just so we're all on the same page, it's aligned with learning target number 6, which is thermodynamics, right? How does heat move around? And it's due December 4th. Normally it would be due on Thanksgiving that Friday, but Thanksgiving, so just push it back away. And so the discussion starts with what is conservation, right? Just that term, conservation. If you're conserving the environment, if you're conserving animals, right? If you're conserving water on a desert island, if you're a conservative party, what does the word conservative mean? And so the answers I got from you, the students, were typically like it means to save or keep steady, that kind of stuff. And that's accurate. If you're conserving the environment, you're saving the environment. If you want to conserve the animals, you're saving the pandas so people could see in the future how useless they are. If you're conserving water on a desert island, you're saving the water for later. If you're a conservative party, you're typically more traditional than other parties. And so that's what conservative means. If you're talking about the conservation of matter, you're saying that matter never changes. If I burn a log, right? If I burn a log and I collect everything that the log gives off, all the smoke, all the charcoal, all the ash, I'll find that it weighs the same amount as my log, even though it changed, but the matter is still the same amounts of matter. And energy is the same way. If I eat a bagel, I'm going to get the energy of that bagel and I could use it to power my brain, to move my heart, to move my legs around, to move my hands like I do all the time in these videos. Energy is conserved. And so the question being asked is, if a hot piece of metal is dropped into some cold water and they eventually equalize their temperatures, how was that energy being lost or gained? And we decided in class that the amount of energy lost by the metal is equal to whatever was gained by the water. It's a 1-to-1 kind of thing. We followed that up by watching a video. I'm not going to show you guys what the video is, mostly because of copyright stuff. Just go ahead and click on that link to watch it. But it's a heat treating video. So in that video, we kind of start talking about specific heat. Specific heat capacity is the capacity of a metal or any kind of object to hold heat, right? At what point does the energy change the temperature, right? Because every object could hold in some amount of heat, and as it does, right, if it holds enough heat, it starts to raise its temperature. So when is that exact point where the energy increases the temperature? That's what specific heat is. And so heat treating a metal makes it stronger, right? The heat of that the metal absorbs enough heat where it gets stronger, and then you immediately dunk it in some oil or water, and that strengthens the metal far more than it naturally would be. And so we're asking whether or not this is an extensive or intensive property. And so a lot of you guys get confused. A lot of you guys said it was extensive. And that's because, yeah, it kind of makes sense. If you have a cup of water or a pool of water, one of those is going to heat up a lot faster. But individually speaking, this is an intensive property because it depends on those bonds between particles, right? How much heat something could hold is dependent on how strong the forces between those particles are. So metals, not very strong. They kind of conduct heat very easily. And so they kind of give energy off willy-nilly. It's very easy to raise the temperature of metal. Water, on the other hand, very hard. Those bonds are very, very strong. And so it's an intensive property. It does not depend on the amount of the material. It depends more on what that material is. And so specific heat is measured in multiple types of units, usually measured in joules per gram times Celsius. And so again, moving on to number 4, which is where we'll top it off right now. Moving on to number 4, we have the specific heat of iron, water, copper, aluminum, right? And what that is just the amount of energy. Remember, amount of energy needed to raise 1 gram by 1 degree. So if I had a gram of water, if I wanted to raise this temperature, I would need 4 joules of energy. If I had a gram of iron, if I wanted to raise this temperature, I would need 0.449 joules of energy. If I had a gram of copper and I want to raise this energy, or raise this temperature, I would need 0.385. So the question being asked is, which substance will raise its temperature the fastest / the most if they were given 50 joules of energy? So doing the math, all we're doing is 50 divided by 4.19. 50 divided by 4.19 means that the temperature of water will raise by 12 degrees. Iron will raise by 111. Copper, which is the one that will raise the most, will raise by 130. And then aluminum will raise by 56. So you can see metals are very good at raising their temperatures when energy is applied. Water, not so much. It's very good at absorbing it, but the temperature doesn't raise. And so for the second part of this question, we use our specific heat to see how much energy is needed to raise the temperature of our material. And so the question is, how much energy do we need to raise 20 grams, about a cup, more or less? No, it's not a cup. 20 grams is like 20 milliliters, which is like probably like a shot glass worth of material, water. So raise 20 grams of material by like 10 degrees Celsius. So we're using this equation. Your book doesn't emphasize the math too much, so I'm choosing not to as well. Normally, I would spend like a week on fiddling with this equation, right? Manipulating it so we could determine all of these different variables in any way, shape, or form. But for now, we're just going to stick with this singular equation. So this equation is saying the heat capacity of whatever substance times the mass times delta T. The triangle stands for delta. T stands for temperature, which is therefore the change in temperature. Triangle stands for change in, will equal the energy. So the specific heat capacity of our material in these units times the mass in grams times the change in temperature will give us the amount of energy that you need. So if I have like a bubble bath and I want it to be warm, I could know how much water is in my bath. I know how much I want to raise the temperature of the water by, and therefore I could calculate the heat, the energy needed to raise my temperature, so to get my water to the perfect amount. That's how we do that. We take the specific heat of water, which is 4.19, over here. That's where I got that from. We take the mass of the water, which is 20 grams. We have 20 grams of each of these guys. And the change in temperature is 10 degrees Celsius. It doesn't matter what the initial temperature was. It could be 5, 10, 15, 20. It doesn't matter. All that matters is that you raise the temperature by 10 degrees. That's what matters. And so to do that, we just multiply all of these together, and our final answer is 838. You guys will do 3 through 4 on your own. And when we come back on Wednesday, Thursday, whenever, we will go ahead and answer the rest. So that's a quick recap of this video of the last 2 days. If you have questions, comments, or concerns, let me know on Schoology or Remind, or shoot me an email. For now, thank you for watching, and I'll see you all later. Bye-bye.